Okay, there we are. Okay, so here we are, lecture number 2. Oops. Okay, I was telling Lenka, and I wanted to tell you, and I will also post it on the Slack, that over the next couple of weeks, as you work on specific projects, if there is anything that I can help you with, I am available. So you just send me a message on Slack, and we set up a time. We have a 7-hour time difference, so it will be in the afternoon for you, but I'm happy to contribute if there are projects that you're working on that overlap with my own expertise. Okay, so today we are going to talk about a different class of, a specific class of models that I think Marc Mézard mentioned, but this is a little bit of a different implementation, and it touches on questions of back propagation through time, and I think it offers a very useful and alternative solution. So because I'm a neuroscientist more than a machine learning person at this point in my life, I want to use a particular example of neuroscience as motivation and application. I will use it again in my last lecture tomorrow. So what we can do nowadays is we can record simultaneously from many neurons. So we can record population activity, and we can do that with this kind of high density multi-electrode arrays that allow us to record of the order of 100 neurons, or we can do it with neuropixels, which allow us to record from the order of 1,000 neurons. And because all these neurons can be recorded simultaneously, then we can use this data to characterize the dynamics of neural circuits. And so time becomes time, and simultaneous recordings becomes a tool for characterizing population dynamics. And I'll show you this data later. We can do these recordings not only in non-human primates, but also in human primates. This is particular recording of 110 neurons of a subject doing a task that I will tell you about, but this is a human subject, not a monkey. So again, of the order of 100 neurons being recorded simultaneously, in this case, during of the order of 20 seconds. Every in this kind of data, every row corresponds to a given neuron. Time is on the horizontal axis, and every tick corresponds to an action potential. So neurons work on the regime of what we call point processes. So these are processes that occur, they are delta functions in time, essentially. They occur over a very narrow period of time, and they are a strong swing in the action potential of the, on the membrane potential of the neuron that emits a spike. So how do we analyze this kind of data? So we consider a population of n neurons. We observe the spiking activity of these neurons with a time interval. Oops, something happened there. A time interval of size of length t. And what we do is we divide these into bins of size delta. So instead of talking about a time t, we talk about a discrete time k, where the capital K is t over delta, and we measure it using an index k, which varies between 1 and capital K. So in each one of these bins, indexed by this discrete time variable k, we observe, we count the number of spikes emitted by neuron I during that time interval. And we call that variable y sub I of k. So y sub I of k, this, for instance, in this case is 4, is the number of spikes emitted by that neuron in that particular time interval. Okay, so that's y sub I of k. And let me consider a very simple task. As I said, I will tell you about a task that I will use today and tomorrow as an illustration. It's called a center out task. So it's very simple. There is a center target, 8 targets that surround it. At some point, a new trial starts because one of these targets is illuminated. Then there is a waiting period that is variable between half a second and a second, between 500 and 1,000 milliseconds. And then the subject, either human or non-human primate, gets a go cue. So you have to wait for the go cue to execute your movement. Once you get the go cue, there are typically 300 milliseconds that you need to respond to this go cue, and then there is a movement onset, and you move your hand to the target, or you move this manipulandum that moves a cursor on a screen and captures the target. It takes of the order of 700 milliseconds to one, let's say 1 second at most to complete this reach. And then you reach the appropriate target, you get rewarded. It's not a memory task. The target is illuminated during the whole duration, during the whole execution of the reach. So it's a very simple task. And as I said, we'll use it today. We'll use it again tomorrow as an illustration of some interesting concepts of what goes on in the brain. So this task was first studied in the early 80s by the lab, from the lab of Georgopoulos. And in this case, the recordings were of single neurons. The ability to record simultaneously from many neurons was not there yet. So every row here corresponds now to a different trial, not to a different neuron. It's always the same neuron that is being recorded. And as you can see, this neuron, first of all, it's very noisy. And noise is one of the important things I want to discuss today. As you can see, there is a lot of trial-to-trial variability. Although, for instance, all these trials, there are here 5 trials that correspond to reaches to the same target. There is a lot of trial-to-trial variability. But at the same time, this neuron is specific, has a tune to direction. So this neuron, for instance, when the trials are to the left, fires more. And when the trials are to the right, it fires less than average. So the firing rate of this neuron is suppressed relative to background when the reaches are to the right, but it's enhanced relative to background when the reaches are to the left. So this neuron has what we call direction selectivity. So there is a specificity to the response of the neuron. It has information about the task, about the purpose of that task, the purpose of that particular trial, the location of the target that is supposed to be reached on that particular trial. But at the same time, there is a lot of variability. So how do we account for the variability? Well, because the number of spikes is a countable, non-negative variable, we suggest using a Poisson distribution. So we suggest that the probability distribution of observing exactly Y spikes, it's a probability distribution that is controlled by a single parameter lambda, and it's of the form lambda to the y e to the minus lambda divided by y factorial. So it's the typical Poisson distribution. This y factorial in the denominator, which does not depend on lambda, is there to make sure that the distribution is properly normalized. So if you sum lambda to the y e to the minus lambda divided by y factorial over all the possible integer non-negative values of y, so y equals 0, 1, 2, all the way to infinity, the e to the minus lambda comes out of the sum because it does not depend on y, and lambda to the y divided by y factorial summed from y equals 0 to infinity, remember y is an integer index, is the Taylor expansion of e to the lambda. So you get e to the minus lambda times e to the plus lambda, which gives you 1. So it's a properly normalized distribution. And if you like to play with this kind of Taylor series, you can compute the mean of y, the expectation value of y, given this distribution, which happens to be lambda. And you can compute the variance. You take y, subtract the mean, square it, and compute the expectation value of that. And again, you get lambda. So the Poisson distribution is a very peculiar distribution in that if you take the ratio of the variance divided by the mean, you get 1, which is, this ratio is called the Fano factor. And one way to check whether the distribution is Poisson, if you're given data and you want to make the assumption that this data is Poisson distributed and you want to check whether your assumption makes sense or not, what you do is you compute the variance, you compute the expectation value empirically on the data. So the mean of the data, the variance of the data, you take the ratio, and if it's sufficiently close to 1, your assumption of Poisson is not such a very bad assumption. It's a reasonable assumption because the Fano factor of your data is close to 1. So the point of view that I'm going to take is this point of view allows me to account for variability and specificity. So lambda I of k would be the mean or the expectation value of y sub I of k. Remember, y sub I of k is the number of spikes emitted by neuron I at time interval k. So y sub I of k is a random variable that has mean lambda I of k. So this random variable fluctuates around its mean, and the fluctuations of the variable around it means describe the variability of neural activity. But we saw that the neural activity has specificity also. So we argue that this parameter lambda I of k is what provides a tool for specificity. We can model lambda I of k, and that's where the generalized linear models will come in, through its relationship to an input to the network, which will be sensory stimuli, the output of the network, which will be motor output, and the spiking activity that happens in between. So for that neuron and for all the other hidden neurons. So that there's going to be an input layer, an output layer, and then a collection of hidden neurons whose activity we will monitor. So we are going to think then of neural activity as a Poisson process. As I said, we have these bins that are of size delta, where delta is T over K. T is the total continuous time, the duration of the experiment. K is the number of bins. And there is an index that is a time discrete variable that labels those bins. And then on that bin, we observe a certain number of spikes for neuron I sub I of K. And it's that particular observation has probability P of Y sub I of K. So what is the data? The data is to know for every bin what was the activity of every neuron in that bin. So our data is this Y sub I of K, where K labels all the bins and I labels all the neurons. And we're going to model this random variable, this stochastic variable, as a Poisson process that has a mean lambda sub I of K. So if the mean is lambda sub I of K, the probability of seeing precisely Y sub I of K spikes is lambda to the Y e to the minus lambda divided by Y factorial. So it's the same Poisson process that we saw before, except that now is neuron specific, the index I, but it's also a Poisson process. The mean of this process varies as a function of time, as the activity or the task is being executed. So if this is the probability for observing, the probability of observing exactly this number of spikes for neuron I at bin K, what is the probability for the whole data? Well, the probability for the observed data is going to be the product of this probability multiplied over all time bins for a given neuron and then multiplied over all neurons. Why can I make this assumption of multiplication of probabilities? Because these probabilities are conditionally independent. What does it mean to make this assumption? It means that all the constraints due to the task are in the lambdas. So the probability of Y given the lambdas, condition on the lambdas, is just about the fluctuations of the Ys. Every Y sub I of K fluctuating around its mean value, lambda I of K. And what I'm assuming is that these fluctuations are independent of each other. So what I'm ignoring when I make this assumption and I write this equation is I'm ignoring the possibility of noise correlations. I'm just saying that all the correlations are described or contained or restricted to the correlations between the lambdas, but then the fluctuations of each Y sub I of K condition on the lambda sub I of K, those fluctuations are independent from neuron to neuron and also from time to time to a given neuron. So because this formula is the probability is the likelihood of the data is rather cumbersome with all these products, what we do is we take the log likelihood. So we take the logarithm of the probability. And so we talk about the likelihood or the log likelihood of the data computed during this time t. We have the log of the product. The log of the product is simply the sum of the logs. So now in the log likelihood, we get the sum over all neurons. And for every neuron, a sum over all time bins of this expression. So what do we get when we take the log of this expression? When we get Y times the log of lambda from this factor, then we get the minus lambda from this factor, and then we get minus the log of the factorial coming from the denominator. So this is an expression, the expression that we get for the log likelihood of the data. So here is again the likelihood, the log likelihood of the observed spikes. And notice, where does the data appear? The data appears here, is the y sub I of k, and it appears here in the logarithm of the y sub I of k factorial. And then the firing rates lambda appear here as the log of lambda and here as lambda. So the y sub I of k are the data, which are neuron-specific index I and time-specific index k, while the lambda sub I of k are the parameters of the model. And you could ask yourself a very simple question, like if I'm giving you the data and I ask how to choose the lambda sub I of k to maximize this likelihood, but you can take the derivative and find the answer to that question. It's actually a little bit obvious, but a little bit surprising. If you are only given this and no other information, what should be your maximum likelihood choice for the parameters lambda sub I of k, which are the parameters of your model? But what we're going to do is to propose a parametrization of this lambda sub I of k that is rather smart, actually. So what our goal is to create a model for this lambda sub I of k. So we're going to find a model for the lambda sub I of k that relates their value to the sensory stimuli, to the motor outputs, and to the activity of all the neurons in the network. So that's the question, how to model this lambda sub I of k. And that's the topic of today's lecture, which is the approach that I'm going to take is to use these generalized linear models. So before I tell you about generalized linear models, I have to take a little mathematical detour into statistics and tell you about probability distributions of the exponential family. But before I do that, this is a good time to stop and ask you if you have questions or if you see where we are headed and what we're trying to do. What we're trying to do is to model the likelihood of data of this type. And we write the likelihood as the likelihood of a Poisson process. When we write it as the likelihood of a Poisson process, we end up with an equation like this, where y sub I of k is our data and lambda sub I of k are the parameters of the model. And now we want to propose a model for these parameters. We want to introduce a parametric model for the lambda sub I of k. So if you have no questions about this, about the philosophy that we're taking or the point of view that we're taking, then I'll take the little detour and tell you about the exponential family of probability distributions. So what are probability distributions? What is the exponential family of probability distributions? Is a family of probability distributions of the following form. Rho sub I, y is the stochastic variable, and rho sub I is the probability density function for that stochastic variable, is described by two parameters, delta and phi. And it has this form, is the exponential of y times delta. Y is your stochastic variable. Delta is a parameter that is called the canonical parameter delta, minus a function b of delta. This still involves, the numerator here only involves the canonical parameter, divided by a function a of phi, where phi is called the dispersion parameter. And then we have an additive term c, that is a function of y and phi. And this term is very important because it provides a tool for normalizing the probability distribution for any value of delta and phi. And there are three functions here that have to be chosen. The function b of delta, which depends only on the canonical parameter delta. The function a of phi, which depends only on the dispersion parameter phi. And this function c of y and phi. So c is a function of the dispersion parameter, but also of the variable y. The variable y appears here and multiplied by delta, and it appears here in the normalization factor. So this term, as I was telling you, c of y and phi plays a very important role because it provides a normalization that guarantees that if you take this rho of y parameterized by delta and phi and integrate it over y, you always get 1, no matter what is your choice of the values of the canonical parameter delta and the dispersion parameter phi. So this is a And
question, Sarah?
yeah,
So if it is a normalization, why does it still depend on the y?
the normalization depends on phi, only on the dispersion parameter, not on delta, but it's a function of y. Because you're integrating this, which is a function of y, and you normalize. So this normalization, I'll show you in this particular case, will be equivalent to this parameter, to this term here. That's what the normalization will do. Is a y factorial, which does not depend on the parameters of the model, depends only on y, only on the stochastic variable in this particular case, and is there to guarantee that this is properly normalized. You need the y factorial to get the normalization. So in this case, it's a function of y, but only of the parameter phi, not of the parameter delta. And you can convince yourself by trying to do this integral and seeing what you would need to have here, how this function will depend on this particular function here. So once we have this function and we adjust this function c of y and phi so that this normalization condition is satisfied for all delta and for all phi, so for all values of the canonical parameter and dispersion parameter, then if we take a derivative of this with respect to delta, we'll get a y from here and a b prime of delta from here. We'll get two terms, but since the total derivative has to be equal to 0, we will get that the expectation value of y has to be equal to b prime of delta. And if we take a second derivative, we'll be able to compute the second moment, the expectation value of y squared. And from that minus the square of the expectation value of y, we can get the variance. And this will be the expression for the variance. Again, you can do this. Derivatives is very simple to do. So what you can see is that the canonical parameter delta fully determines the expectation value of the stochastic variable through the derivative b prime of delta, through the function b of delta. The variance, in contrast, requires the dispersion parameter phi, and that appears through a of phi. Okay, so this is, so if you have an exponential family, you have a function that belongs to the exponential family, a probability distribution that belongs to the exponential family. You can normalize it using C. This function b of delta gives you the mean. The b prime of delta gives you the mean, and b double prime of delta and a of phi determine the variance. So why would you care about this particular class of exponential distributions with canonical parameter delta and dispersion parameter phi? Why would you care about this probability distribution of this form? Because most of the probability distributions that you care about, and the normal distribution, the Gaussian distribution, the Bernoulli, the binomial, the multinomial, Poisson, gamma, geometric distribution, chi-square, beta distribution, and a few other distributions are all belong to this class. So what this means is that if I give you a probability distribution and you can write it in this form, you don't need to compute the mean and the variance. You know what the mean and the variance are going to be, because once you identify b of delta and you identify a of phi, you know what the mean and the variance are going to be without doing any more complicated integrals over y to compute the first and the second moment of the stochastic variable y. In particular, we had the Poisson distribution, which was the probability of y given lambda was lambda to the y, e to the minus lambda divided by y squared. I can write this as the exponential of y log y minus lambda minus log y factorial. So now if I compare this expression with this expression, what do I see? I have a y times delta. Well, y times log lambda. That means that delta has to be log lambda. Then I have minus lambda. That means that b of delta, which appears here, is lambda. And because delta is the log of lambda, lambda is e to the delta. So that's the form of b of delta. B of delta is going to be a to the delta. I don't have a denominator, which means that A of phi is equal to 1. And then this term, which is the normalization term, does not depend on phi. Clearly, phi is not needed for this distribution. And the C of phi and y is just simply minus the log of y factorial. So we can read out the functions A of phi is equal to 1, this particular Poisson distribution as a member of the exponential family does not meet the dispersion parameter. Delta is log lambda, or lambda is e to the delta. B of delta is e to the delta. And then this the normalization factor, or the normalization term, I should say, once you exponentiate it, comes from the log of, is minus the log of y factorial. It shouldn't be very surprising that the Poisson distribution does not need a dispersion parameter, because we know that the mean and the variance are equal, and they are both equal to lambda. So it should be intuitive that it's a one parameter distribution and not a two parameter distribution. And in this case, we think of lambda as the parameter of a Poisson distribution. In the language of the exponential family, the correct parameter is delta, which is the log of lambda. That's the canonical parameter for the Poisson distribution, if you think of it as a member of the exponential family. So another way of identifying these values of these functions B of delta and A of phi is to remember that for any probability density within the exponential family, the expectation value of y is B prime of delta, and the variance of y is A of phi times B double prime of delta. So for the Poisson case, the expectation value, which should be B prime of delta, has to be equal to lambda. And the variance, which is A of phi times B double prime of delta, should also be equal to lambda. So from this, clearly, A of phi cannot depend on phi. So we can choose it to be a constant. We will choose to be equal to 1, A of phi equal to 1. And if the first derivative of B of delta is lambda, and the second derivative of B of delta is also lambda, is because B of delta is an exponential. So B of delta is e to the delta, which is equal to lambda. So this is another way of establishing the connections between lambda, which is the parameter of the Poisson distribution, and these functions A of phi and B of delta that allow us to identify the Poisson distribution as a member of the exponential family. Okay, so that's my little detour on exponential probability densities and the family of exponential distributions. And now I want to go back to a generalized linear model. So a generalized linear model is a model for a probability distribution that is a member of the exponential function. And we know that as a member of the exponential function, the expectation value of the variable is related to this function B of delta. It's actually B prime of delta. So the idea of this is to model delta, the canonical parameter, as a linear combination of all the explanatory variables. The explanatory variables would be the input, the output, and all the activity of all the hidden units in your artificial neural network or biological neural network. But if you model delta as a linear function of all this, there is still a nonlinearity in the model, and the nonlinearity is going to come from satisfying this equation. But the interesting thing is that when we write down artificial neural networks, we choose a nonlinearity. We choose to work with a sigmoidal nonlinearity or an exponential nonlinearity or a rectified linear nonlinearity. In this formulation of the generalized linear models, the expectation value is, as I said, related to the canonical parameter by this Lick function G. So because E of y is B prime of delta, there is a nonlinear function G applied to E of y that can give me delta, so that E of y is G to the minus 1 of delta. And this is going to be the only nonlinearity in the model. The interesting thing is that this nonlinearity cannot be chosen independently. It's determined by the statistics. So what is a nonlinearity in the Poisson case? Well, in the Poisson case, delta is the log of lambda. Lambda is e to the delta. Because delta is the log of lambda, delta is the log of the expectation of y. So the nonlinear function that I have to apply to the expectation in order to get the canonical parameter lambda is a logarithm. So lambda, which is e of y, is exponential of delta, and delta, which is g of y, is the log of lambda. So the link function is a logarithm, and the nonlinearity that I apply to delta in order to get lambda is g to the minus 1 is the exponential. So the nonlinearity that we must use in the Poisson case is an exponential nonlinearity. It's very interesting that the nonlinearity, for instance, if instead of a Poisson case, you were talking about such short beams that the number of spikes can only be either 0 or 1. So now you're back to a Bernoulli variable instead of a Poisson variable. Then for a Bernoulli variable, the nonlinearity would be a sigmoidal function. So we are used to thinking in artificial neural networks that these are arbitrary decisions that we make to facilitate the training or to postulate something about the nature of the variables. We know that the variables can only be 0 or 1, and we interpret the sigmoidal as the probability of being in the one state. Or we know that the variable is countable but non-negative, so we think, oh, okay, so let's take an exponential to make sure that it can never take negative values. But the interesting thing is that within this approach of generalized linear models, making an assumption about a nonlinearity is implicitly making an assumption about the statistical nature of the data. What are the fluctuations? Are there Poisson? Are there Bernoulli? Are there Gaussian fluctuations? And reciprocally, once you make an assumption about the nature of those, the statistical nature of those fluctuations, the nonlinearity is determined for you. You lose the ability to choose the nonlinearity independently. You can think of it as a loss. I think of it as a great advantage, which is the nonlinearity can be chosen within a rigorous manner within this formulation, as opposed to being an arbitrary choice of the person who designs the network architecture. So here we are in the Poisson case. Delta is the log of lambda. Lambda is e to the delta. So if I want to model lambda, what I need to do is write down a linear model for delta, and then say lambda is the exponential of delta. So lambda is e to the delta, or in other words, I'm modeling linearly, not lambda, but the log of lambda. The log of lambda, which is delta, is the canonical parameter, which I'm going to model as a linear combination. And that's of linear combination of all the observed variables that are explanatory variables that can explain the random variable y, explain it in the sense of explaining its mean, because the fluctuations of y around its mean, which is lambda, are determined by the fact that I said that y is a Poisson variable. So I know the probability distribution of those fluctuations. So just to summarize what we're going to do for the rest of the talk. So we have a log likelihood for these spikes, and the log likelihood was the sum over all the time beings for a given neuron, and then over all the neurons of the activity y sub I of k observing that time b, the log of lambda I of k, that's a parameter, minus lambda I of k, that's again a parameter, minus the log of y factorial. So the parameter lambda I of k is a mean, but it's a time-dependent mean, so it's a Poisson process. I cannot look at the whole row for neuron I and say there is a lambda. I cannot compute the mean for that row, because that would be ignoring the fact that this mean is actually time varying. So I'm talking about the Poisson process. But if I use this generalized linear model formulation and I accept my assumption of a Poisson distribution for the spikes, then it's not this mean, but it's the logarithm of the mean, which gives me delta, and the logarithm is a link function that is going to be expressed as a linear combination of all the observed variables that can be used to explain the observed firing rates. And these observed variables are internal covariates, internal to my measurements. These are the preceding neural activity, the activity of all the hidden neurons, and the external covariates, which are the input-output pairs, the sensory stimulus, which are the inputs in the case of the brain, and the direction of motion, which are the outputs in the case of this simple task that I showed you before. So let's talk about these covariates, internal covariates and external covariates. Maybe before I do that, that's another good place to stop and ask you if you have any questions of what we're going to do.
No questions at this point. Are there? No questions, sir.
No questions?
No.
Okay. So where we are headed is to use this structure of the generalized Young models to apply it to the particular example that I was showing you before. So we have a plot like this raster plot. So we know for these n neurons that we're measuring, we know the spiking history of the ensemble of n neurons up to the current time t. So let's say it's a recurrent neural network model, and we know what has been happening in this recurrent neural network up to now. We know how many spikes every one of these neurons has emitted in every one of these time intervals, every one of these beams of size delta. So we call this the spiking history at time t. The spiking history at time t is a collection of the y sub I of t prime for all t prime preceding t and for all the neurons I from 1 to n. So given this information, what is our expectation of the number of spikes a neuron I will fire in the interval between t and t plus delta? That's precisely lambda I of t if I divide by delta. So it's a conditional intensity lambda I of t. It has to be a strictly positive function. It's the history-dependent generalization of the time-dependent rate of an inhomogeneous Poisson process. So lambda I is actually a number of spikes in observing the beam, but I've divided by the size of the beam in milliseconds or seconds, and I get a rate. So this is why I'm going back and forth between the language of number of spikes or rate. The important thing to remember is that this is going to be time dependent. So I want to model lambda sub I of t if all that I know, I don't know what were the inputs, I don't know what were the outputs, I don't know what was the task. I'm running a recurrent neural network over time, and I'm gathering data. And given the history of the spiking of this recurrent neural network, I am just trying to predict what is going to be the activity in the next time beam, given that I know what it has been doing in the immediate past. So I'm going to trying to model this lambda I of t, condition on the history, meaning the history is the data that I have to model lambda I of t, and we are going to use this generalized Young model formulation. So as I said, we take delta, which is the log of lambda. So delta at time t, given the history and given parameters alpha, which is the log of lambda at time t, given the history and given parameters alpha, I'm going to model as a linear combination. A linear combination of what? What is the data that I can use? Well, the data that I can use is the fact that I've been accumulating information about what the neurons in that recurrent neural network have been doing. So what I know is the activity of neuron J for all neurons, J from 1 to n, for preceding times. So not only at time t, but time t minus 1, t minus 2, t minus 3, all the way up to t minus tau. So I have a history dependence here. So it's like a recurrent network, and it's like a time-dependent process. I'm looking at the dynamics of this network. And of course, I don't go all the way to, I don't have an infinite memory. I have a memory that is tau steps, and I call it tau sub n because it's a memory over neural steps. So I want to predict what happens at t, given that I know what has happened at t minus 1, t minus 2, all the way up to t minus tau. And the influence that neuron J at time t minus n has on neuron I and time t is a weight, it's a coupling that I call alpha ij of m. So it's from neuron J to neuron I at a time lag of m. So neuron I at time t, neuron J at time t minus m. And the alpha ij depends only on m. And I'm adding an alpha I0, which is just like a background firing rate to the model. So what I'm doing then, because this is a model for the log of lambda, I'm simply rewriting this saying my model for lambda then, for lambda for neuron I at time t, given the history, which is my data, and given these parameters alpha, which I need to determine, is going to be an exponential function of this linear combination. The linear combination is a background term, and then it takes into account the influence of all the other neurons, including itself. The sum from J equals 1 to n includes the term for I. That means to say, I'm going to use the history of the firing patterns of the particular neuron also as information to predict what this neuron will do at time t. And as I said, these are weights, the alpha I, this is a bias, the alpha I0, it's a bias for neuron I, and the alpha IJs are weights in my model that quantify alpha IJ of m, quantifies the effect that neuron J at time t minus m has on the spiking activity of neuron I at time t, from t minus m to t, or beam t minus m to t, and it depends only on m. It depends only on the time difference between these two processes. So this is the structure of a GLM. I said, if I have a neuron A and a neuron B, and I want to determine the firing activity of neuron A, what I do is I look at its past weighted by these coefficients alpha ij of m, but I also look at what neuron B has been doing, and I weight it according to these coefficients alpha ij of m. This weighted sum is just a linear combination that is passed through this exponential nonlinearity. And this exponential nonlinearity gives me lambda. Lambda is the mean of a Poisson process. So if I want to transform that into spikes, I need to have Poisson dice. I need to have a stochastic process that generates a certain number of spikes, which is going to be the value of y, the number of spikes emitted by neuron A at time t, given lambda. And the same thing for neuron B. Neuron B looks at its own past, but it also gets information about what neuron A has been up to. It filters that past data according to these coefficients alpha ij of m. Alpha ij of m are like kernels essentially in this sum that are used to weight as we look into the past for this information. And the linear combination again is passed through this exponential nonlinearity in order to throw a Poisson dice and generate spikes. So for instance, let's say I have these 4 neurons that are connected in this way. The blue neuron influences the red and the green. The red neuron influences the purple and the green. The green neuron only influences the purple. And I write these kernels. So the diagonal elements are each neuron looking at its own history. And the non-diagonal elements are how each neuron influences. So the red influences the green according to this kernel, but the green does not influence the red. So from the green to the red, the kernel is 0. In the same way that from the purple to the red, the kernel is 0. The red only receives input from the blue. So this is a connectivity matrix, but it's a time-dependent connectivity matrix. It doesn't tell you just how neuron J influences neuron I, but how neuron J influences neuron I at time t minus 1, t minus 2, t minus 3, all the way to t minus tau. And we can see then a connectivity pattern, but we can see also the dynamics of those interactions. These are like, you can think of this as time-dependent synaptic coefficients. So now we use our maximum likelihood approach. So as I told you before, given the data, also value of k, we wanted to find parameters, lambda I of k, that maximize the likelihood. And I'm writing the likelihood of the data again, the log likelihood as the sum over neurons, sum over time beings of y log lambda minus lambda. There was an extra term that was minus the log of y factorial, but I'm not adding that term because I need to maximize this in the space of the lambdas. So the last term, in this case, did not depend on lambda, and so it has been dropped. And now we have a model for the lambdas. Our model is that the log of lambda is this particular linear combination. So if you substitute the log of lambda here by this linear combination and the lambda as the exponential of this combination, you can write the log likelihood, the likelihood of the data in terms of these parameters alpha. This is my generalized linear model. So I want to find the parameters alpha that maximize the log likelihood, which is the sum over neurons, sum over time beings of y times log lambda. Log lambda is this linear combination minus lambda. Lambda is the exponential of the linear combination. So this is our generalized linear model. And what we are asked to do is to find the alphas that satisfy this model. So I'm going to show you two very interesting things about this maximization. I'm going to show you how it is similar to backpropagation through time, but yet not exactly like backpropagation to time, and what's the advantage of that. And the second thing that I'm going to show you, which is very surprising to me when I first learned about this class of models, is that this log likelihood function is always a convex function. It has a second derivative that is non-negative. And therefore, when you try to maximize this likelihood using a gradient ascent method, you will never have to worry about falling into or landing into a maximum, which is not the global maximum. There is only one maximum, and that is the global maximum. So let's look at how we would go about doing gradient ascent in this case. So again, we have this network of neurons. Oops, I have a dangling parenthesis there. Sorry, I'll correct it and propose. Y sub I of k for all the neurons I from between 1 and n, and all the time in scale. And this is our generalized linear model. Right, so this is the likelihood of the data given the parameters of the model. And what we want to do is find the maximum likelihood parameters, we would call alpha star, using an iterative gradient ascent method. And if we are really sophisticated, we want to use an adaptive step that is controlled by the second derivative. So to implement this algorithm, we need to compute the first derivative of the likelihood to have the gradient ascent term, and the second derivative of the likelihood also with respect to the parameters, if we want to actually use that Hessian information in order to use an adaptive learning step. So if you do the gradient, you find something really, really interesting. So we take the gradient of this likelihood with respect to an S of j of m. Remember that this is a parameter, the connection from neuron j to neuron I at the time lag m. So this goes from neuron j to neuron I, and it has this form. It's a sum over all time steps of. This is the activity of the presynaptic neuron. And I'm using this word presynaptic and postsynaptic. I have italicized them because this alpha ij, I don't mean biologically to imply that it's really a synaptic strength. It's just a connection, it's a lag-dependent connection in the network. But y sub I of j is the neuron on which this connection originates, and it's y sub j at time k minus m. And then it relates to y sub I at k, so that the time lag is m. But this is a presynaptic activity, but this is not a postsynaptic activity. It's a difference between what the postsynaptic activity actually is and my current prediction of that postsynaptic activity. Mu is an index that says how many times I have iterated the gradient. So mu is my current estimate of the parameters. And with my current estimate of the parameters, I can predict what I think the activity of neuron I is going to be at time k. And so this has the form of a presynaptic activity times a postsynaptic error. So presynaptic activity times postsynaptic error is our famous delta rule. But notice that I didn't have to backpropagate this. because there is a direct connection from neuron J to neuron I at time delta. And this direct connection is for all neurons, but also for all time lags M. So by allowing for this connection to be not just one number, but a series of numbers that define this kind of kernels that I showed you here, this kind of weights in a linear combination that are time dependent, I get a waiver from the problem of doing backpropagation through time. And by getting a waiver from doing backpropagation to time, I also get a waiver from the problem of the vanishing gradient. This model doesn't suffer from the problem of the vanishing gradient. And the reason for not suffering for the problem of the vanishing gradient is that it's like having a direct connection from every hidden unit to the output, so that you can say, well, this is the error at the output, the difference between what the output should be and what I'm currently predicting the output to be, times the activity of this neuron. That's how I need to adjust the weight. That's the contribution to the gradient. And by having these direct connections from hidden layers to the output, we avoid the problem of backpropagation. We avoid the problem of the cumulative factors of the derivative of the nonlinear function, which leads to this vanishing gradient problem. So by allowing for these time-dependent or interactions that are explicitly dependent on the lag, we increase the number of parameters in the network. Let's say if we are going to allow for 10 time lags, so each weight is actually a 10-dimensional. It has 10 parameters in order to characterize that time dependence or time lag dependent synapse. But the advantage that we gain is that we can obtain the gradient relative to all these weights and update all these weights, all the coefficients in this kernel, without having to worry about vanishing gradient problems. The other great advantage of this method we notice when we compute the second derivative. So now, first of all, notice that the parameters only appear here. The parameters only appear on the y sub I of k. The y sub I of k depends on the alpha ij of m for all j's and for all m's, but not for a different I. So when you take a second derivative, you're going to take a second derivative of this form. The alpha ij of m, alpha of the same I, j prime, m prime. So I prime, that derivative will be 0. The coefficient I prime different from I doesn't appear in the first derivative, and therefore the second derivative would be 0. So now what we get is a minus sign, a sum again over time lags, y sub I of k. Y sub I of k is my current prediction. This expectation value at time mu is my current prediction of what neuron I will be doing at time k. This is at time 2 presynaptic activities. What neuron J was doing m time steps ago, and what neuron J prime was doing m prime time steps ago, which is consistent with the fact that I have the alpha ij of m. So from J to I with the time lag of m, and then from J prime to I with a time lag of m prime. So I have 2 presynaptic activities at my current prediction. Now, all these activities are Poisson variables. All the variables y represent a number of spikes emitted during a Binet size delta. So all these are non-negative integers. So y sub j is a non-negative integer, y sub j prime is a non-negative integer, and my current prediction is an exponential of something, so it's also a non-negative variable. So these 3 variables are all non-negative, their product is non-negative, but there is a minus sign in front. So every component of this Hessian matrix is negative, and this surface is everywhere convex. So that's the other great advantage of using this formulation as opposed to backpropagation through time or recurrent neural networks, is that as we train the network, we don't have to worry about finding local maxima that are not the global maxima. It's a convex surface. So now we have an algorithm. The algorithm can be written in the following form, that if I have the value of the parameters alpha, alpha is a listing of all the parameters that I need to specify the model. If I want to go from step mu to step mu plus 1, I update using the gradient of L computed at time mu. This is the gradient of the likelihood function L, which is obtained by taking the derivative with respect to every parameter in alpha. That's the derivative that looks like a delta rule. It's very similar to doing backpropagation. And then we can use, then we have not minus the gradient, but plus the gradient. We are going to do gradient ascent in the likelihood function instead of gradient descent. And then we have this matrix, which is the inverse of the Hessian, that we invert the matrix of steps of the Hessian matrix to obtain adaptive steps. So if we had p parameters that were needed to specify the model, alpha is a p-dimensional vector, the gradient is a p-dimensional vector, and the Hessian is a p by p matrix that needs to be inverted to obtain a matrix of adaptive time steps. You don't have to be so computationally expensive. You could use just a diagonal approximation to the Hessian and then invert it, ignore all the off-diagonal terms, or you could decide not to use an adaptive time step. As I said, it's not so crucial to use an adaptive time step because of the fact that the second derivative is always negative. The matrix of second derivatives, all the components of this matrix are negative, and therefore we are talking about a concave function. So, so this is the philosophy that we're going to adopt. And now I want to show you again, I want to go back to my simple example of this central task and show you what happens to when you take advantage of this kind of modeling. So again, these are these multi-electrode arrays that allow us to record simultaneously from 100 neurons. I know that they are all theories, but just for your information, this is 4 millimeters by 4 millimeters. The distance between adjacent electrodes is 400 microns. And what you do is you cut the dura, you cut the bone, and then you implant these electrodes on the surface of the primary motor cortex, in front of the sulcus, essentially. And the data that I will use for this is from this human data that I showed you before, which was, this was 2 human clinical participants with tetraplegia, and they were doing this task while sort of under neural guidance. So the cursor was being moved on the screen not by their hand, which they couldn't move, but by their neural activity. So they would imagine doing the task, and we would record neural activity. So let's start by looking at the dynamics of the network. So this is the data that looks like, as I showed you much earlier. This is the data that looks like this. This is 110 neurons from primary motor cortex M1, human subject 3. This is what this data looks like from the human subject. So we take this data and we write down our model. What is it? I know the history. I monitor up to time t-1, and I ask, what is the probability that neuron I spikes at bin k, conditioned on the spiking history during the preceding 100 milliseconds. So we know how to write this. We have an equation for log lambda for neuron I at time k, giving the preceding history. And we know that it's an alpha I0. This is the neuron looking at itself in the past. So this is neuron I looking at itself at time k-1, k-2, k-3, all the way up to tau bins. And then this is neuron I looking at all the other neurons. So now I'm separating the self contribution from the others contributions, the network contribution. And now this sum then is for j different from I, and again, alpha ij at time k minus 1, k minus 2, all the way to k minus 5. So in this analysis, I've taken a very, very small time being, just 1 millisecond. So the number of spikes is going to be either 0 or 1. So they're going to be a spike, which means 1 with probability p, and then 0 with probability 1 minus p. So the mean value, lambda, is equal to p. The lambda is 1 times p plus 0 times 1 minus p, so it's p. So to model lambda, to model the mean, in this case, is equal to modeling the probability that there will be a spike within this 1 millisecond beat. Neurons have a refractory period, so after they fire, there is a time that it takes before they can fire again. And this time is of the order of a couple of milliseconds, 1 to 2 milliseconds. So if you've been at 1 millisecond, you will only see no spikes or 1 spike at most. And what I'm going to do is look 100 milliseconds into the past. So if I am in this bean, I'm going to look at 100 beans into the past, because every bean is 1 millisecond. So I'm going to fit my GLM, and that will allow me to extract alpha I0, which is the background level of the spiking activity of neuron I, alpha II, which is the neuron I looking at its past history, is how the preceding activity, the preceding firing activity of neuron I gives me information about what neuron I is likely to do in the future. And then the alpha IJs, which are the connectivities, which are how the spiking activity of other neurons preceding the current time will affect the spiking activity of this neuron. So I can feed the model in the way that I told you. And once I feed the model, then I can actually look at what it tells me. I know that is the estimated probability of a spike for any neuron I at any time k. So how do I feed the model? Okay, so I have a current value of the parameters. Given the current value of the parameters and the data, I construct my current estimate of a neuron I would do at time k. That's my current value of my current estimate of lambda, my current estimate of the probability of spiking in this case. And it's going to be the exponential of the alpha I0 current estimate, and then the sum over all other neurons, including over all neurons, including myself, j prime from 1 to n, m prime from 1 to tau n, of this particular linear combination, where again, these are my current estimates of the weights, and this is the data. So once I have computed these estimates, I don't need to look at the alphas anymore, because the gradient, I can build now the gradient, and I can build the Hessian. Why can I build the gradient? Because this is data. This is my current estimate of what neuron I will do at time k, which I have already computed. So I don't need the alphas anymore. I'm just only storing this. And then this is data. So that's my current estimate of that particular component of the gradient at time mu. Time mu, I mean iteration mu in my gradient ascent algorithm. And then I can build the components of the Hessian matrix. Again, this is data. This is what neuron J was doing m time steps ago. This is what neuron J prime was doing m prime time steps ago. And this is my current estimate of a neuron I will do at time k. So I get the Hessian, and I invert it to the matrix of second derivatives to obtain a matrix of step sizes, of adaptive step sizes. And then I just use my equation, in which the new value of the parameters are the all values of the parameters plus the adaptive step size matrix times the gradient. And so I get these temporal filters. And instead of plotting the alphas, I will plot the gammas, because remember that lambda is e to the alphas. So, and I'm interested in lambda. So I'll plot e to the alphas, which is the gammas. So this is gamma now is in the form of a gain, and the gain can be larger than 1, so be a real gain, or smaller than 1, which is an attenuation. So this is a very interesting plot for the intrinsic history. So this is neuron I looking at itself into the past. This is 100 milliseconds into the past. Remember that I beamed at 1 millisecond and I allowed the model to look 100 time steps into the past. So this initial depression, yeah? Oh, I thought there was a question. This initial depression is a refractory period. So after a spike has been emitted, the probability of emitting another spike starts at 0. It takes a while to grow. So there is a typical interspike interval of the order of 20 milliseconds. Then there is again a suppression, and then there is a large facilitation. And then there is a lot of ensembles if you look at how neuron I is receiving input from neuron J. And we have done very interesting work comparing these kernels, parameters of the model for human data, compared it to the monkey data. And in primary motor cortex for this very simple task is surprisingly similar. So it's very interesting. Another interesting thing to note is that this effect of interactions really peters out at 100 milliseconds, which means if it had ended at significant values, it would have been an indication that we needed to look further into the past, but we don't really need to look further into the past. So this is for the intrinsic history of the network. That is to say, if I am observing the dynamics of my recurrent neural network, of my self-connected neural network, without knowing anything about inputs or outputs, what can I say? So this is in some sense the unsupervised learning part of the learning the dynamics of the networks and being able to predict as a generative model, predict the subsequent dynamics given the time step. And you can run this actually as a generative model, because if I give you a history of 100 steps, now you can predict the 101, and then from that and the preceding data, you can predict the 102, and then you can run it as a generative model of a network that hopefully has the same statistics as your original network, the network that generated the data, be it an artificial network or a biological network. So let me go back to this task and remind you of what we saw before about the specificity. So Georgopoulos in the early 80s found a lot of neurons that had this property that the firing was intensified for reaches in a given direction and then suppressed for reaches in a different direction, but it's a very broad tuning function. And so he proposed to plot the firing rate of this neuron by looking at a wide interval. He looked at 300 milliseconds around 0, where 0 is actually the goal cue. So the animal has already prepared to do the movement. He has been observing the target for a while, and at the goal cue, then he's ready to let go. So for these 300 milliseconds, we count the number of spikes divided by 300, we get a rate, and then we get 8 points clearly because there are only 8 directions of motion. And for this particular neuron, we get this particular curve. And what Georgopoulos proposed was to characterize a reach in the direction theta and a reach of an extension r by a cosine tuning curve. It has 3 parameters. It has a preferred direction theta I, which is the direction in which the neuron fires maximally, and then a cosine modulation about it. So cosine of theta minus theta I. The cosine of theta minus theta I will range from -1 to 1. So we add a 1 to it. Now it ranges from 0 to 2. We divide by 2. So now this ranges between 0 and 1. And we multiply by a sub I, which is the amplitude of the modulation. And we also multiply by r, because larger reaches of a larger extent will increase the modulation of the firing rate. And then, of course, we add to it V sub I, where V sub I is a background activity. So we have a background activity and then an amplitude of fluctuations around it, and the fluctuations have, the tuning curve has this cosine form. So this is just 3 parameters: background activity, amplitude of modulation, and preferred direction to characterize the tuning curve. So we want to include in our GLM this direction of motion. So of course I could use the same trick as I used before, which is to try to correlate the firing activity now to the motion during 100 milliseconds or 200 milliseconds into the future. But instead of doing that, I'm going to use a known fact for these real neural networks, which is that the motion lags by about 150 milliseconds the activity that we record in motor cortex. So what I'm going to do is very simple. I'm going to consider three possible models. In one model, I only look at tuned networks that are cosine tuned. And I said, what is going to be the logarithm of the firing rate? What is going to be the logarithm of the firing rate of neuron I at time t? Well, it's going to be the alpha I0 plus, and then I use the Georgopoulos formula, 1/2 of an alpha IR. So now this is a modulation of the reach. The value of the reach, which is going to be a tau t plus tau r. So this is a reach subsequent to the firing rate. The reach follows the firing rate by 150 milliseconds. And then I have 1 plus the cosine of theta, which is the direction of the reach. So the reach is defining these polar coordinates, direction of the reach at time t plus tau r, and extent of the reach at time t plus tau r. And the parameters are going to be alpha I0, alpha IR, and theta I, which is the preferred direction for that neuron. I could be a bit more sophisticated and add to this the fact that each neuron has a firing pattern. So I could add to this term the history of neuron I. So I could say, well, let me add to it the alpha II of m times the activity of neuron I at time t minus m, and sum again into the past, look into the past for the duration tau n, where tau n now is my neural window as opposed to my reaching window. Or I could allow the neurons to interact and make this last term even more sophisticated by allowing not only the neurons, a neuron to look at its own past, but to look also at the past history, firing history of all the other neurons. So I have three ways of constructing a model that allows for this. So the data that I'm going to show you now is data from monkeys. So this is this multi-electrode arrays in the arm area of primary motor cortex of monkeys that are awake and behaving. And the task is not just this very simple 8-target task, but it's just a tracking. So now the reaches are still 2-dimensional, but the reaches can be in any direction and of any length. So it's a tracking of a moving visual target. The target moves, you have to capture it, the target moves again, and you have to capture it. And you use this manipulandum that I showed you earlier to move the dot on the screen and capture the targets. So the hand movements are constrained to a horizontal plane using the manipulandum. The target moves, the cursor moves in this 2-dimensional plane, and you can then find the position, XY, digitize it, and you can use a different final difference model, compute velocity. So we will compare two models, a simple velocity model and the velocity plus a spiking history, but just only the autoregressive spiking history. So this is the velocity model. The velocity model says, okay, what is going to be the probability of neuron I spiking at time t, given the velocity at time t plus tau, the direction of motion at time t plus tau, and there are going to be three parameters: an alpha I0, which is the background, an alpha IX, which is the coefficient by which the x component of the velocity is multiplied, and the alpha IY. And if we write again the velocity in polar coordinates, what we get is the absolute value of the velocity that comes out, and we get the alpha IX multiplying the cosine of the direction of motion, and the alpha IY multiplying the sine of the direction of motion. And as I told you before, we are not summing over time lags. There's a single time shift, which would take to be 150 milliseconds, because that's a typical time lag. I had some problems with some of the questions. I'm sorry, I'll fix it and I will repose. There are 3 parameters to be determined through the maximum likelihood, which is the background, the contribution of the x component of velocity, and the contribution of the y component of velocity. So I do my gradient ascent, I find this, and now I can do plots in which I plot the lambda I plot the probability of spiking as a function of theta and v, because now I know the coefficients alpha I0, alpha IX, and alpha IY. So I can do these plots, and this is for 3 times 4, 12 different neurons. The horizontal axis is the velocity in centimeters per second, the speed at which the cursor is moving. The horizontal axis is theta, is the direction of the ridge between minus pi and pi. And the color code indicates the number of spikes during this 300 millisecond window. And you know, the range is different for different neurons. But what is interesting is to see, first of all, this cosine. If you cut for a given value of the speed, you see the cosine modulation, you see the wide peak and then the 2 suppressed regions. You see the variety of parameters theta I that we're finding, the different preferred directions that come out of the modeling, and also the fact that the modulation is much more marked once the velocity has reached a given threshold. While if the speed of motion is very low, if you look at the parameters are low speed of motion, then you will not see this modulation with direction. So let me now be a little bit more sophisticated and write the same model that we wrote before with alpha I0, alpha IX, alpha and Y, but add the autoregressive component. That is to say, add to it the sum of alpha II of m, y sub I t minus m. So this is a neuron looking at its own past history, again at bins of 1 millisecond. And this time resolution, the number of spikes can only be either 0 or 1. So I'm asking whether the neuron will or will not spike. Now I have, of course, more parameters because I not only have the 3 parameters for the Georgopoulos part of the model, the part that correlates direction of motion and speed of motion, but I also have the parameters for the autoregressive filter. And in this case, we took not 100 milliseconds, but 120 milliseconds into the past. And this is what we get for a typical neuron. For a typical neuron, we get the velocity tuning curve, which again has this Georgopoulos cosine tuning, and it's enhanced as we increase the velocity. But we also get this autoregressive kernel, and what the autoregressive kernel shows is the refractory period. So once the neuron has fired, if it has fired at t minus 1, t minus 2, t minus 3, up to t minus 18, it's unlikely that it will fire again. It has a very strong suppressive effect. And then it has a facilitation effect, but the facilitation effect only lasts up to 60 milliseconds. Beyond that is null. So, so we have a suppression for 18 milliseconds, a peak at about 30 milliseconds, and then no effect beyond 60 milliseconds. That is to say that by extending my period of observation and seeing how this filter goes to 0, I can evaluate how long into the past are there autocorrelations in the firing of this neuron. How long into the past is what the neuron did in the past will give me information about what the neuron is likely to do now. And I want to finish actually by showing you this, because it's a very, it's really a very interesting tool, particularly for Poisson processes, which is called the time resampling theorem. So if I look at the times where neuron J emitted 2 spikes, so it did the spike at time J minus 1 and at time J. And I integrated simply time, simply du from Tj minus 1 to Tj. That integral will give me the interspike interval, will give me the interval between the spike number j minus 1 and the spike number j. So I will get e to the minus the interspike interval, and I construct this new variable, which is 1 minus e to the minus the interspike interval. Now the interspike interval for a Poisson process is going to be a stochastic variable that has an exponential distribution. If I have the correct lambda, I can use that to rescale time. So instead of integrating time to compute the time interval between the spike j minus 1 and the spike j to subsequent spikes, I can now actually integrate using lambda as a way to rescale the time. And the idea is that if this is my correct model, then my variable z is going to be a stochastic variable that has a uniform distribution around 1. So I can use this to test for the self-consistency of my model. I started by assuming that the model was Poisson. And then I have different ways of trying to model the lambda of that Poisson process. And I can ask, how good is my model for the lambda of that Poisson process? And this is a way to test for that, to use the time rescaling theorem to check how close I'm coming to getting a stochastic variable that is uniformly distributed around 1. So I'm showing you here results for the two models that I just constructed here. First, simply a model that correlates the spike firing to the reaches without any knowing of the history. And then the autoregressive model where I added this term so that I not only have a connection to the external variate, which is the direction of motion and the speed of motion, but I also have a connection or information about the firing history of that particular neuron. And this is the difference. This is the improvement due to actually finding, including this history. So when I don't include the history, I get the green curve. The green curve is for the velocity model only, and the blue curve is when I add to the velocity model the autoregressive part of the spiky history. This is still, I'm not taking into account the connection between neurons. I'm only taking into account information that I gain by knowing the spiking activity of that neuron into the past. So what happens to the velocity model? The velocity model is pretty bad. The velocity model overestimates lambda for up to 10 milliseconds after the spike. So this is when the spike was emitted, and for 10 milliseconds there is a gross overestimation, and then it underestimates, beyond 40 milliseconds after the spike is underestimating the value of lambda. On the negative, or the correlation coefficients, the autoregressive coefficient significantly corrects for that. And I still have a little bit of a problem here, but I almost eliminate the subsequent underestimation of the density lambda. So this idea of point processes and the time rescaling theorem, which are ideas that Emory Brown proposed about, I would say, 15 years ago or so, are very powerful ideas to investigate all these point processes, all the processes that occur as singular events in time, which is what happens when you allow for spiking neural networks as opposed to rate-based neural networks. So this is the summary of what I wanted to tell you today. So these generalized neural models give you a principled approach. Why is it principled? Because you don't have to make an arbitrary choice of the nonlinearity. It's a principled and a systematic approach to modeling the time-dependent rate of it's an inhomogeneous Poisson process. It's a Poisson process with a time, with a rate, with a mean value of the number of spikes per second that is time-dependent. And this allows me to describe the expected firing activity of the neural example. So it takes account of all the part that we call the specificity. I can condition that specificity on the history. I can condition on external inputs. I can condition it on external outputs. So they can be internal covariates or external covariates. So if I only focus on the internal covariates, then the logarithm I model in a linear fashion, not the time-dependent rate, but the logarithm of lambda. This is what I am allowed to model in the context of generalized models, and I model it linearly, and each can be a linear combination of the intrinsic covariates, which are the preceding finding activities of that neuron and all the other neurons of the ensemble, and extrinsic covariates, which are the preceding input stimulus or the subsequent output activity observables. And the likelihood of the data is log convex. The optimal model parameters follow from a gradient ascent algorithm, which is totally unambiguous. So the problems that you avoid as compared to recurrent neural networks and backpropagation through time by taking the point of view of Gerardian models is that you don't have local maxima, you only have a global maximum. And the other problem that you avoid by allowing for these connections that go directly from the hidden unit to the output unit is that you avoid the problem of the vanishing gradient. So this is a tool that was very well known in engineering, but not very well known in the mathematics of it, certainly not for computational neuroscientists, which is what I am. And the reason why I wanted to make you aware of this tool is because I think that if you're interested in recurrent neural networks or backpropagation through time, this is a more principled approach and a problem that avoids some of the computational difficulties that arise when you want to. It allows you to control the history. I decide in a recurrent neural network, I don't control how far back into the past these influences go. But when I want to do a learning on a recurrent neural network or using backpropagation through time, then we run into serious problems about vanishing gradient problems, which you avoid in this case. And that's it. That's all I wanted to tell you today.
Thank you, Sara. So do we have some questions? Go on. I will repeat it.
So as an intuition behind the generalized linear model, is it an assumption just for computation?
Is it what?
I mean, is a linear assumption used for the computational efficiency?
Yeah. The question is whether the assumption of linearity of these log lambdas is just for computational efficiency, or whether there are some other reasons.
This model is in a class of what is called linear nonlinear models. It's like if you wanted to do a single layer perceptron, right? So you do a linear combination and then you apply a nonlinearity. The nonlinearity could be a sigmoidal if you want to have a graded perceptron, or could be a step function if you want to have a binary perceptron. But it's just a single, in some sense, it's a single layer linearities followed by a single nonlinearity. So it's a linear nonlinear model. So it's a choice. I mean, I could make a more so there is a nonlinearity that is fixed by the choice of statistics. Once you say Poisson, you have to take the log of lambda. That's it. So lambda is e to the whatever. Now, how you model the log of lambda could be more complicated than linear. So then you make the choice of, you say, okay, I already took care of one nonlinearity, and now from now on, for the rest of it, I will make a linear assumption. So you choose to model the log of lambda as a linear combination of all the covariates or the explanatory variables. You could make a more sophisticated model where you have nested nonlinearities, right? But if you do that, then you lose the theorems, you lose the properties that I showed you.
I had a question about how actually the results depend on the size of the bin in the time.
Say it again.
I was wondering how the results that you showed us depend on the size of the bin of the time window.
Right. So that's a very good question. So I think that Let me share again. So if you look at this, so this curve has been traced at the resolution of 1 millisecond by looking at 120 milliseconds into the past. If you use beams of 1 millisecond, then there is a crucial difference, because at 1 millisecond, you can either have 0 spikes or 1 spike, and the process becomes a Bernoulli process, and the nonlinearity becomes a sigmoidal. But once you allow for larger, not at the single spike resolution, but at the multiple spike resolutions, by using larger windows, larger deltas, larger beams, then you immediately go into the Poisson regime, even if you're not going to observe a 100 spike. So it's a question of time resolution. Do I need to trace this curve at 1 millisecond resolution, or can I trace it as a lower resolution? And now, once I have done this work, and I can see, first of all, I don't need to go more than 60 milliseconds into the past, and maybe I don't need to trace it at the 1 millisecond resolution. So once I gain information about the system, am I asking questions at the 1 millisecond level or at the 50 millisecond level? And I can give you answers in the neuroscience context. For instance, if you are going to use your ears for source localization, like an owl does, then I need to know very precisely the time difference between when the signal arrived to my left ear and when the signal arrived to my right ear, to know whether it came from over there or from over there. And I need to know this is done on the first spike received by the right versus the left, And a barn owl can detect this at even some millisecond resolution. If I'm working in primary motor cortex, these signals, this firing activity of the neurons in primary motor cortex, these neurons connect directly to neurons in your spinal cord that are called motor neurons, which connect directly to the muscles. The muscles are elastic and have an inertia. The muscles don't respond immediately. The muscles don't respond to single spikes. The muscles have an inertia of the order of 50 to 100 milliseconds. So I don't need to know the exact time when spikes were emitted at the millisecond resolution. If I'm talking about M1, I can look at the system with a 20, we usually been at 20 milliseconds or even 50 milliseconds. And we are fine if we're trying to predict behavior, because the behavior implies muscle contraction, and the muscles have a response time that allows the muscle to, forces the muscle to integrate over many spikes over a time period. So I would say that depending on the problem that you're studying, that determines the time resolution in which you need to look at the network. And that determines your choice of beam. Now, the methods do not depend on the size of the beam. There will be more computational expense. It will be computationally more expensive when you decide to work at a low resolution, at a very high resolution with a very small beam size.
Okay. Just noticing there is a lizard listening to your lecture. Interesting. I have another question, maybe because I was wondering about actually how dense are the neurons that we are measuring. In essence, these coefficients alpha ij, should I think about them as like direct interaction of a neuron I with J, or is it some kind of effective interaction because I'm just like...
It's an effective, that's a great question. This is why I was trying to be very careful when I talk about presynaptic and postsynaptic, because there isn't the synapses from neuron J to neuron I. These electrodes are separated 400 microns. 400 microns is a big distance in terms of neurons. So also it's a subsampling problem. You know, when I make a rich movement like this, of the order of 1 million neurons in my primary motor cortex are being co-modulated by this task. I'm putting an electrode that samples 100 of them. So clearly the interactions is like a big soup of neurons, and I'm putting an electrode here and an electrode here and an electrode there. So clearly the interactions that I'm measuring are effective interactions that are mediated by many neurons. And this is why it makes sense to consider different timescales, because there could be a very quick path, a very short path that allows neuron J to influence neuron I at a short time lag. And there could be another long path that allows neuron J to influence neuron I via at a longer time lag. So the idea of an alpha ij that depends on M and extends 60 milliseconds into the past is also depending on this idea of an effective interaction. Even the self-interactions could be effective. You know, neuron I talk to neuron K that talk back to neuron I. So now neuron I has a reference to its own history more milliseconds into the past than a single synapse would have allowed.
Okay, okay. Are there other questions? Anyone? If not, thanks again. And it seems there are no other questions. So thank you.
Okay.
A lot, Sara.
I'll see you tomorrow, and we'll talk about dimensionality reduction, linear and nonlinear tomorrow.
Okay, great.
Okay,
Great.
great. Enjoy. Bye-bye. See you tomorrow.
Thanks. All right. Thanks.